the other component, the personal computer, this will receive all the vital sign information from the child, and it'll also be where the user transmits commands, like it wants to view the data that's been recorded, this and that. Like I said, the software will be loaded onto the computer. It does a couple functions, like it will validate this user's credentials, store the recorded data from the infant onto the hard drive, and it'll send user commands. And to display all the results and put in the commands, just the computer's display for the user will be used for that. And the functions that it'll do: view vital sign readings, store data, view error messages, alarms, and emergency contact information if the alarm should go off, they know to contact them. And this here is a architecture of that. The inputted data is coming streaming wirelessly here, and that'll go through the computer. And there's also the hard drive there where things will be stored. You've got the user on top, where you get your commands, and all of the outputs will be then transmitted over to that monitor for the system. And this here is just a picture of the whole thing put together, how it'll all interact. And you see like how the data flow moves through that.
This is what we came up here for a use case diagram to show all the users involved and what their responsibilities are. Probably the most obvious one is the child user will actually be wearing the garment and doesn't have much responsibilities other than to live and just produce the signals. And then we have the primary user that has all of the responsibilities and is able to actually add and remove users to the system. Is able to set threshold value parameters for all of the sensors for each child that will be registered to the system. And they are also able to add and remove children if they have more than one child that would like to use the system. Secondary user is able to do most of these functions as well. However, they will not be allowed to set child parameters, mainly because it won't be their child that they're looking over. This is mainly for maybe babysitters or grandparents, such of that nature. This is our state diagram here. Kind of shows how everything will play around with the system. So it'll, once the system is turned on, it'll remain idle until some actions are being taken, and it will start reading temperature sensing, and pulse sensing, respiration. If those are required to be read, they're done. We also have a data store where we'll constantly be doing storage for 48 hours or so and place the data on the read. And it will set sound an alarm if any of the 3 sensors go out of the threshold values that were preset for each child. There's a display that will display error messages, such as if a user enters a wrong username or a wrong password. Also, if they don't fill out a required section for maybe information, content information, or parameters. And each error message will show a message describing the error as well, what needs to be fixed. And yeah, if it is turned off, then it won't read data because generally the garment won't be worn once the system is off. So.
Now that our system has been described and the architecture has been shown, I once had an instructor who said that no program or no system actually fully operates as it should. It just hasn't met the data that's made it crash yet. So that's why we introduced testing. And why is testing important? Basically, the engineering requirements that Ann presented earlier must be verifiable. And testing helps us do this. And the statistics show that as the timeline of the project and of the system actually advances, the cost increases exponentially of changing designs and things like that due to errors that could have been prevented due to testing. So basically it minimalizes cost, which is definitely a good thing. Also, using testing, you can find the boundary points of operation of your system. And when you define these boundary points, you can make sure that your system operates correctly at them. And if it doesn't, you can provide a means to correct specific errors that can happen here. So basically, there's several different types of testing. Black box testing is when you have no knowledge of the actual internal workings of the system. So basically, you have the system in a black box, you fool around with the inputs, and you see what happens with the outputs. And you try to change the inputs as much as possible so that you can compare all of the outputs to your desired expected outputs. White box testing is when you actually target the internal nodes of the system. So we have several sensors. We have the pulse sensor, the temperature sensor, and the respiration sensors. You can target these actual specific nodes using white box testing and make sure that they are operating as they should. And the way you do this is you can control two things called controllability and observability. Controllability is when you actually have the ability to take one of these nodes and make it remain constant, and then you can monitor the output that way. And observability is how well you can actually observe the outputs of these nodes after you change the inputs. We'll be doing a type of white box testing. It's actually considered acceptance testing. And when you do acceptance testing for a system, you're actually delineating conditions under which the customer is going to accept the system, which that's definitely important. So basically, this is just an example of one of our specific modules for acceptance testing. This is one of our system functions that will mainly be used by the user, which will be either primary or secondary user, and it's going to allow them to add users. Basically, this test table shows different scenarios here. The first one being valid, meaning what types of correct inputs they're going to provide. It's going to be the type of user, the username, contact phone number, username, and password. And basically, if they give all of this input correctly, then the system is going to create that user and store their data in system files. And then there are several instances when the user may accidentally add one of the wrong types of input, or they may do it incorrectly, such as they have an invalid type of user, one that doesn't exist. There's primary, secondary, and child. If they enter anything else, they're going to have a problem. And the system's basically for each of these errors is going to display an error message saying, you know, this input doesn't match up correctly, and it's going to let them try again, basically. We're also going to be performing software tests for our system. And basically, software tests step through the specific use cases that are going to be encountered by the users of the system. So as the user uses the system, it's going to encounter specific aspects of the software. Basically, it provides a means of handling errors, and it shines light on areas where the system actually does not operate how you expect it to. So it's not necessarily an error, it's just you thought it was going to work one way and it actually doesn't satisfy that requirement. This is an example of one of our software tests. Basically, the use case scenario that we are using for this table is load/view stored data. So once the data has been collected from the infant and has been stored, you can load and view it on the computer. And it looks almost similar to the acceptance test. You have a valid case and then several invalid cases. And basically, the user's logged in, the user is primary user. Those are both valid inputs. And basically, the system is going to allow the user to select a date, which is going to be in folder format, and then it will display these the required information that the user wants to see.
All right. What we're hoping to make is an efficient system so that it doesn't take a lot of power. It can be powered with a very small battery. And we want it to be effective.